So this is the second part of the lecture 5. So let me begin with a couple of observations. Maybe let's make another corollary before we start examples. Corollary. Suppose f of z is equal p of z divided by q of z, where we have here that p of z0 is defined and is not equal to 0, q of z0 is equal to 0, and we assume that none of those functions q and t are not and the q of z is not equal to 0 identically, and also assume that p of z and q of z are analytic around z0. So then, because of the fact that we have here a division by 0, we have that f of z has a pole at z0 of the order that is equal to the order, let's say to the multiplicity of 0 for multiplicity of 0 z0 for q of z. I know this sounds a little messy, complicated. Let me just simply write it down like this. So we have here f of z. Using formulae very often help a lot. So this is pz, this is q of z. So here we know that p of z0 is not equal to 0. But q of z0 is equal to 0. So we have here a situation in which we have a division by 0. That clearly means that z0 does not belong to the domain of f, and this is an isolated, because other points are okay. Because every 0 of an analytic function, this is an analytic function, both of them, so every 0 is isolated. So in this case, that 0 is an isolated singularity. So in order to determine the type of this singularity, we just look at that one and say, yes, it comes from a 0 of an analytic function. So this is an analytic, this is 0. So this is analytic, division by an analytic function, so it must be a pole. And then you look at what kind of pole, so you can write it down. Q of z can be written, this is the multiplicity of the 0s to the power n, you pull it out, and then you have another function, g of z, and here g of z0 is different than 0, so that means you took out from the expansion of the function q of z the maximal possible factor z to the z0m, and this is the order of pole, and this is order of 0, z0 of the function q of z. So this is order of pole of f of z. Notice that in such a case, it is absolutely not necessary to consider the function p. Just look Once you check that this is not equal to 0, in such a case, just simply concentrate your attention on the function q of z, and let's start the examples to illustrate this particular situation. So let me do first the couple of the, let's say, okay, let's do it that one. So examples. For a given function f of z, find all singular points determine which of them are isolated and next determine their type. So that means this is for the isolated singular points, either removable singularity, either Paul or essential singularity. Removable singularity, Paul, essential singularity. There are no third possibility for isolated. If something is not isolated, so in such a case, we do not really proceed further. That's simply non-isolated, so that's it. So we are not interested. So solutions. So start with A. So our A will be, for example, the function which was mentioned above. So this is z is equal to the cosine of z, and that one is 1 minus e to the power z. Notice that this function, here is a function p of z, which is equal, let's see what it is equal. This is cosine of z, and the function q of z is equal to 1 minus e to the z. So the singular points of f of z are the zeros, so that means are the zeros of q of z. So that means the zero singular point of f, if 1 minus e to the z 0 is equal to 0. And that one, of course, means the following, that this equation is the same as e z 0 is equal to 1. So you know how to solve it. You just simply write, and this will be log, and this is log, this is multi-valued log. There are infinitely many solutions to it. So we know what it is. This is I 2 pi n, and we are getting here n belongs to the integer numbers. So how many singular points we have? Infinitely many. Each of them is isolated. So maybe if you don't see why they're isolated, so let me make a small drawing. So this is my complex plane C. So of course we can put here like this. This is my value here, 2 pi I. Then I have here 2 times pi I, 2. So this will be 4 pi I. This will be 6 pi I. And those are the singular points. All of them. Infinitely many. So singular points, I put here like this. Singular points are, and I put here z is equal I 2 pi n, where n is equal 0 plus minus 1 plus minus 2 and so on. So infinitely many singular points. Since they are all separated, you see, they're all separated, So they're all are isolated singular points. So we know that these points are isolated. So now we need to check their characters. So take n is z0. So take n is z0, and they're infinity, so we just don't discriminate. We just simply write 2 pi n. So then we need that p of z, what is this p of z? Is equal to, let me see. P of z is a cosine. Very nice. This is cosine, and I put here I 2 pi n. And what do I get here if I put here cosine I? Interesting. What is this cosine 2 pi I? So I'm getting here that this is nothing else than this is cosine hyperbolic 2 pi n. And it is clear they're all non-zero. Actually, if you remember what was the cosine hyperbolic looking like, so cosine hyperbolic looks like that. That's a curve. At 0 is 1, at everywhere else. So cosine hyperbolic for real values is always positive. So here we have no problem. This function is never 0. And the q of z of z0, put it like this, this is z0, is of course equal 0. But let me compute q prime at this particular point. So what do I get here? Q prime is the derivative. So I take this value here and I'm taking minus. So I'm getting here this is equal to the minus, and this is e to the z0. But we already know what it is, because e to the z0 is equal to 1. So it is equal minus 1. And this is for all z0 equals to I 2 pi n. So we are getting here, that implies that this point is a simple pole. Z0 is a simple pole for every, let's say Z0 equals 2 pi ni for every n belonging to Z. So this is a simple pole. Why? Because this is a zero multiplicity. Maybe I should use red. It would be too messy if multiplicity of z0 is 1. So that means it's a simple multiplicity, simple pole, simple multiplicity, simple pole. Very good. So we got all the poles are simple points, simple poles in this case. Let me do the following, and let me find the following. So let me say the b, I will check a little different function. I will put it like this, f of z is equal, I put it again, cosine of z, and here I put here 1 minus e, and this is 1 divided by z. 1 divided by z. Let me look at that one. Let me look at this one. Notice that what are the singular points? Of f of z. It's clear. A. So to call it like this, I. Notice that since division by 0 is forbidden, I have definitely one singular point which is equal to 0. You cannot divide by 0, so that means it's not possible. It did not have it here. So then let's see, are there, how many points are other points? How many solutions this equation has? Is equal to 0. So that means 1 is equal to E1 over Z. And this, we solved it before, so that means simply we can write it down. 1 over z is equal log of 1, and that one we already know this one was equal I 2 pi n. So that implies that z is equal 1 over I times 2 pi n, and I'll leave it like it is. So we can say that those are also singular points. So those are also singular points. So z0. So let me list. So all the singular points, all the singular points are all the singular points of zz, or f of z are, and we have here like this. z0 is equal to 1, and second we call it like this 0, or we put it is equal 1 over I 2 pi n. Notice, call this points just simply n. So those are also singular points. So I put here n because n can be equal like cannot be 0, so it has plus minus 1 plus minus 2 and so on. And you notice that this zn has this property that if you take limit of zn, n goes to infinity, then you will be getting here this one. Let's look what it is. This is going to be 1 divided by 2 pi n. Sorry. Limit as n goes to infinity, 1 divided by 2 pi n, which is 0. So that means this is my z0. So if z0 is a limit point, that means the point z0 equals 0 is not an isolated singular point of f of z. Notice, on the other hand, if you take the function of cosine, apply it of 1 over I 2 pi n, you will get that this is again the cosine hyperbole of 1 over 2 pi n, and that, as we showed, was positive, so we do not have here any problem with this particular point z0. For z0 is equal 1 over I 2 pi n. So I need to determine what is the multiplicity of the, take the function q of z is equal to 1 minus e to the minus 1 of z, and let's compute the derivative of this function. So I'm getting here, this one is equal e to the 1 over z times, and this is 1 over z squared. That's the derivative. So if I plug it in now, the values 1 over I 2 pi n, so I'm getting here that the first value is exactly 1, and the second value is equal to 2 pi n divided by I squared. So I'm getting here that this is minus 4 pi square n square. Okay, so this one, it's messy. Let's try to erase this messy part. Is equal, so this is minus, because I square is minus 4 pi square n square larger than 0, sorry, smaller than, different than 0, that's enough. We are getting here that Zn, 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 and we are getting here that the point Zn is equal 1 divided by I 2 pi n, which is exactly minus I divided by 2 pi n, is a simple pole. Simple pole, yes, because we are getting multiplicity, so simple pole. This means multiplicity 1, that means it is 1, first derivative 1. And we got the second problem solved. So let's do another problem, C. What about the function f of z is equal sine 1 over z? So here again we have only z0 equals to 0 is the only singular point. If it is the only one, so of course it's isolated. And we also have here that sine of 1 over z around that point has the Lorentz series expansion that can be easily constructed. This is minus 1 over n, and then you have here 1 divided by 2n plus 1 factorial times z to the power 2n plus 1. I just plugged it instead of z. I plugged 1 over z, got that one. So you have here infinite. This is actually equals to, you start with 1 plus, and this is p of z. The principal part starts with n is equal 1, so the principal part, so this is infinite principal part, which means nothing else that the z0 equals to 0 is an essential singularity. Is an essential singularity. So let me maybe look at something different and let's say maybe try to do something like another example for something else. So let me do it like this. I put here z to the power 2, put it like this, cosine of z, and here I have here sine square z. Here we have here definitely infinitely many singular points, so put it like this. Singular points are those which are zeros, so that means you look at the sine square of z is equal to 0. Those are giving you, that means sine of z must be equal to 0. So singular points are z. I can put it like this, n, because there are infinitely many of them. So this is n equals zn equals, and we know this is pi n. Sine of z 0 if z is equal to pi n. So that's it. So this one is pi n. And then n, of course, is equal to 0 plus minus 1 plus minus 2, etc. Notice here that here we have the numerator, but for numerator the situation is not so clear, because if you put here cosine of zn, so this will be equal cosine of pi n, you are getting this is minus 1 to the power n. This is not equal to 0. This is okay, but z square, actually for n is equal 0, z square, basically gives you, you see, another 0, so that means this case should be treated separately. So I would say like this: since z0 is equal to 0 appears in both cases, so you see you have here a 0 at the top and 0 at the bottom, so we should take it separately. We should take it since 0, so we should consider the function. So we can just simply consider the function. Write it down: f of z equals, I put here g of z, and that one will be z squared divided by sine square z. And that one is times cosine of z. So I just simply call that function. So call this function g of z would be just z squared sine square of z. Consider the function of z where, so that means singularity of f of z sits here. So I just take that one, and I know that one is non-zero around none of those singularities. It doesn't count. So this cosine is not playing any role in the determining the type of the singularities. Only the important information is contained in the function g of z, and this can be done easily. So we need to notice that. So we assume, look here, and you see you have here two functions. One is analytic, another one is analytic. So that means this is analytic function around all those singular points. So I'm pretty sure this is going to be a pole. There is no division by 0 except the division of the 0 of the function. So we will look at this one. We will check if the function g of z has a pole at zn. So we start with the point z0. So let's do it like this. So put it like this: 1 over g of z is equal, and I put here, this is sine square of z, this is z square. And now I will do a little trick. I will just simply say this is z square, and I sine, I can put it like this. This will be 1, and I put a few terms of the power series with respect to z of the sine. So what do I get here? I'm getting here, this one is equal. Sorry, this is not correct. This one is z minus z cubed divided by 3 plus z 5 divided by 5 factorial. No, minus, and then 3 dots, everything square. So let me go down, and you see this becomes a little easier to do it, because now I can take this z out. So here is the square, so this is square, and now I take this z out and put here to square, so this is z square. That's two things, and I'm having here the inside of that one will be 1 minus z square 3 factorial plus z 4 5 factorial minus everything square. So of course, look, this is an analytic function because the power series is convergent here. Moreover, notice this function, I call this h of z. So this h of z square. So you see this function here, maybe let's denote it differently, phi of z. So this is the inside. It gives you analytic function such that phi of 0 is different than 0 because it starts with 1. So that square, this will be square, I call it h of z. Together with the square, this will be h of z. So what do I see here? I'm getting here this and this cancels, and I'm getting here that that one is equal, this one is equal h of z, and we know that h of 0, actually we can write it down, it is equal to 1, is different than 0. So since this function is not 0 at 0, so we can say that g of z, which is equal 1 over h of z, is also analytic at z0. That means simply the principal power must be 0. That's principal. There are no powers, negative powers. There is no pole. So that means you are getting here that this is the function. So this z0 equals 0 is a movable singularity. Another way to do it is, of course, you can say the limit. So let me do the another way. So you just simply take limit as z goes to 0 of f of z, and let's check what happens here. So let's check it. So what do I have here? I have here z square. So this is z square sine square of z times cosine of z. And what do I get? I'm getting here, this is, of course, sorry. Limit as z goes to 0, z square divided by sine square z times limit z goes to 0 cosine of z. So now the first one is equal to, okay, this is the same. You can use L'Hopital if you want, but you know exactly. This is limit z goes to 0, and this limit sine z over z to the power minus 2 times 1. So this is 1 times 1 is equal to 0. How do I know that this limit is 1? Because we know that the derivative of sine is cosine, and that means this limit must be equal to 1. Otherwise, we will not get it. Or you can use the power series expansion to find out what is the first coefficient of the power series expansion at this function, which was done above. Remember, sine of z, derivative is cosine of z, and sine, so cosine at z at 0 is 1. That's exactly this limit. Okay, so this is the that part of the example. Cancel. I just want to go to the next portion, and maybe let's do a couple of more, because points we have here Zn as well, which is equal pi n. N belongs, okay, let's write it down. N equals plus minus 1 plus minus 2, etc. And again, we already checked for cosine, so we need to write it down that my function f of z will be equal. So I have here z to square times cosine of z divided by sine square of z, and here call the numerator p of z, denominator is q of z. We already know that p of zn, okay, is not equal to 0. It is clear because pi n square times minus 1 to the power n, it is not equal to 0, and q of zn is equal to 0, but q prime of z, which is equal to sine z cosine z, which is of course sine of 2z. And now you plug it in q of pi n. What do I get? I'm getting this is sine of 2 pi n is still 0, by the second derivative of z will be equal to cosine of 2z, and now you plug it in. Q double prime of Zn, so that means Q double prime of pi n is equal to cosine of 2 pi n, which is equal to different than 0. So we have here the multiplicity. Please maybe change it to red one. Multiplicity. So this is multiplicity is equal to 2. You see, this is 2 second derivative, so the pole, so z0 is a pole of order 2. So this is a pole of order, sorry, not z0, zn. Zn for n equals plus minus 1 plus minus 2. Zn is equal to pi n. Good. So we have that one, and let me check if we could do another one. Let me maybe point out CD. What about the function f of z is equal 1 divided by sine 1 over z? So again, you have to find the singular points. So what are the singular points? I know how to find them. We have here sine of 1 over z. So first of all, z0 will be equal to 0. You cannot divide by 0, and of course you have to solve this inequality, so that means 1 over z is equal to pi n, where n is equal, cannot be 0, so this is plus minus 1, plus minus 2, etc. So you are getting here zn is equal 1 over pi n. So you can see immediately by the similar argument as we did before, since Zn converges to 0 as n is converging to infinity, which is my Z0, so that's also a singular point, and those are also singular points. Those are singular points, and this is also singular point, so this is all singular points. So Z0, which is equal to 0, Z0 equals 0, not an isolated singularity, and that means simply you need to consider for Zn. So what happens for Zn in such a case? Let me put it like this: f of z is equal to 1 divided by sine of 1 over z. So this is my function, so just simply 1 is my simply p of z is just simply 1, and q of z is that one. So that one is equal to 1, but q of z, I say this one is equal sine 1 over z. And now let's compute the derivative of this. Q prime of z will be equal minus 1 over z squared times cosine 1 over z. Then I put it like this: 1 q prime of which one? Of 1 over pi n is the same as minus, and this one is equal pi square n square, and this is cosine of pi n, which gives me minus pi square n square minus 1 to the power n, and that clearly n is equal plus minus 1 plus minus 2 blah blah blah. So that one is not 0, so you are getting here again using the same argument before, that this is a simple pole, because that one is multiplicity equals 1. This is multiplicity of Zn. This is Zn is equal 1 to, pi n. This is 1. So the the function, this function has exactly infinitely many simple poles and one singularity which is not isolated singular. All the others are isolated. If to show you exactly where they are located, maybe look again at the axis. So here we have here, for example, take 1 over pi, this is 1 over pi, then we have here 1 over 2 pi, so 1 over 2 pi, and this is 1 over 3 pi, 1 over 3 pi, etc., infinitely many, but each of them is separated, you see, no other points, singular points around it. On the other side is exactly the same. So they are going infinitely many of those. So you see, maybe change it like this. Each of them is separate. So that is maybe enough for a moment. I promise we'll do more examples. These computations, this determination of the character of the type of singularities will play important role in the further development of the computational techniques, especially the techniques which we will be calling the residue method of the residues. And for a moment it is enough, and let's finish the lecture 5, and I hope we can also talk, let's say, soon on Zoom, and if you have any questions regarding my presentation, and if you have any suggestions, or you could like to, let's say, you need more explanations, so I will be happy to provide you with the additional time and we can talk about it. Thank you very much. So